Everyone, it's Clover from 19. Today is day 10 on my challenge day. Now let's start. Today I'm gonna learn building blocks of deep neural networks and forward and backward propagation in neural network, and then about learning hyperparameters and hyperparameters. After that, clarification for what does this have to do with the brain selection. Okay.
In the earlier videos from this week, as well as from the videos from the past several weeks, you've already seen the basic building blocks of forward propagation and back propagation, the key components you need to implement a deep neural network. Let's see how you can put these components together to build your deep net. Here's a network with a few layers. Let's pick one layer and look at the computations focusing on just that layer for now. So for layer L, you have some parameters WL and BL. And for the forward prop, you will input deactivations A, L minus 1 from the previous layer, and output AL. So the way we did this previously was you compute ZL equals WL times AL minus 1 plus BL, and then AL equals G of ZL, right? So that's how you go from the input AL minus 1 to the output AL. And it turns out that for later use, it'll be useful to also cache the value ZL. So let me include this cache as well, because storing the value ZL will be useful for for the back propagation step later. And then for the backward step, or really for the back propagation step, again focusing on the computation for this layer L, you're going to implement a function that inputs dA of L and outputs dA L minus 1. And just to flesh out the details, the input is actually dA of L as well as the cache. So you have available to you the value of ZL that you computed. And then in addition to outputting DAL minus 1, you will output the gradients you want in order to implement gradient descent for learning. Okay, so this is the basic structure of how you implement this forward step. I'm going to call it a forward function as well as this backward step, which call a backward function. So just to summarize, in layer L, you're going to have the forward step or the forward prop or the forward function, input AL minus 1 and output AL. And in order to make this computation, you need to use WL and BL. And it'll also output a cache which contains ZL. Right? And then the backward function used in the backprop step will be another function that now inputs dA of L and outputs dA L minus 1. So it tells you, given the derivatives with respect to these activations, that's dA of L, what are the derivatives, or how much do I wish AL minus 1 changes? So compute the derivatives with respect to deactivations from the previous layer. Within this box, right, you need to use WL and BL. And it turns out along the way, you end up computing DZL. And then this box, this backward function, can also output DWL and DBL. But I was sometimes using red arrows to denote the backward iteration. So if you prefer, we could draw these arrows in red. So if you can implement, so if I'm using red arrows to denote the backward iteration. So if you prefer, we could draw these arrows in red. So if you can implement these two functions, then the basic computation of the neural network will be as follows. You're going to take the input features A0, feed that in, and that will compute the activations of the first layer. Let's call that A1. And to do that, you needed W1 and B1. And then we'll also, cache away Z1. Right? Now, having done that, you feed that to the second layer, and then using W2 and B2, you're going to compute the activations of the next layer, A2, and so on, until eventually you end up outputting a capital L, which is equal to Y hat. And along the way, we cached all of these values Z. So that's the forward propagation step. Now, for the back propagation step, what we're going to do will be a backward sequence of iterations in which you are going backward and computing gradients like so. So we're just going to feed in here dA of L, and then this box will give us dA of L minus 1, and so on until we get dA 2, dA 1. You could actually get one more output to compute dA0, but this is derivative with respect to your input features, which is not useful, at least for training the weights of these supervised neural networks. So you could just stop it there. But along the way, backprop also ends up outputting DWL, DBL, right? Just use the parameters WL and BL. This would output DW3, DB3, and so on. So you end up computing all the derivatives you need. And so just to maybe fill in the structure of this a little bit more, right? These boxes will use those parameters as well. WL, BL. And it turns out that that we'll see later that inside these boxes will end up computing these z's as well. So one iteration of training for a neural network involves starting with a neural network involves so one iteration as well. So one iteration of training for a neural network involves starting with a0, which is x, and going through forward prop as follows, computing y hat, and then using that to compute this, and then back prop, right, doing that. And now you have all these derivative terms. And so, W will get updated as W minus the learning rate times DW, right, for each of the layers. And similarly, for B, right? Now that you've computed backprop and have all these derivatives. So that's one iteration of gradient descent for your neural network. Now, before moving on, just one more implementational detail. Conceptually, it'll be useful to think of the cache here as storing the value of Z for the backward functions. But when you implement this, and you see this in the programming exercise, when you implement this, you find that the cache may be a convenient way to get this value of the parameters of W1, B1 into the backward function as well. So in the programming exercise, you actually store in the cache Z as well as W and B, right? So to store Z2, W2, B2. But from an implementational standpoint, I just find this a convenient way to just get the parameters copied to where you need to use them later when you're computing backpropagation. So that's just an implementational detail that you see when you do the programming exercise. So you've now seen what are the basic building blocks for implementing a deep neural network. In each layer, there's a forward propagation step, and there's a corresponding backward propagation step, and there's a cache to pass information from one to the other. In the next video, we'll talk about how you can actually implement these building blocks. Let's go on to the next video. In the previous video, you saw the basic blocks of implementing a deep neural network, a forward propagation step for each layer and a corresponding backward propagation step. Let's see how you can actually implement these steps. We'll start with forward propagation. Recall that what this will do is input AL-1 and output AL and the cache ZL. And we just said that from implementational point of view, maybe we'll cache WL and BL as well, just to make the functions call a bit easier in the programming exercise. And so the equations for this should already look familiar. The way to implement a forward function and BL as well, just to make the, and we just said that from implementational point of view, maybe we'll cache WL and BL as well, just to make the functions call a bit easier in the programming exercise. And so the equations for this should already look familiar. The way to implement a forward function is just this, equals WL times AL minus 1 plus BL, and then AL equals the activation function applied to Z. And if you want a vectorized implementation, then it's just that times a l minus 1 plus b, with the b, adding b being Python broadcasting, and al equals g apply element-wise to z. And you remember on the diagram for the forward step, right, we had this chain of boxes going forward. So you initialize that with feeding in a0, which is equal to x. So you initialize this. Really, what is the input to the first one, right? It's really a0, which is the input features to either for one training example, if you're doing one example at a time, or a capital 0, the entire training set, if you're processing the entire training set at a time. So that's the input to the first forward function in the chain, and then just repeating this allows you to compute forward propagation from left to right. Next, let's talk about the backward propagation step. Here, your goal is to input DAL and output DAL minus 1 and DWL and DB. Let me just write out the steps you need to compute these things. DZL is equal to DAL, element-wise product with G of L prime Z of L. And then to compute the derivatives, dWL equals DZL times A of L minus 1. I didn't explicitly put that in the cache, but it turns out you need this as well. And then dBL is equal to DZL. And finally, dA of L minus 1 is equal to WL transpose times DZL. Okay? And I don't want to go through the detailed derivation for this, but it turns out that if you take this definition for dA and plug it in here, then you get the same formula as we had in the previous week for how you compute DZL as a function of the previous DZL. In fact, well, if I just plug that in here, you end up that DZL is equal to WL plus 1 transpose DZL plus 1 as, as a function. Okay? And I don't want to go through the detailed derivation for this, but it turns out that if you take this definition for dA and plug it in here, then you get the same formula as we had in the previous week for how you compute DZL as a function of the previous DZL. In fact, well, if I just plug that in here, you end up that DZL is equal to WL plus 1 transpose DZL plus 1 times GL prime Z of L. I know this looks like a lot of algebra. You could actually double check for yourself that this is the equation we had written down for backpropagation last week when we were doing a neural network with just a single hidden layer. And as a reminder, this times is element-wise product, but so all you need is those four equations to implement your backward function. And then finally, I'll just write out the vectorized version. So the first line becomes dzl equals dal element-wise product with gl prime of zl. Maybe no surprise there. dwl becomes 1 over m dzl times a l minus 1 transpose. And then dbl becomes 1 over m np dot sum dzl, and then axis equals 1. Keep dims equals true. We talked about the use of np dot sum in the previous week to compute db. And then finally, dA, L minus 1, is WL transpose times dz of L. So this allows you to input this quantity, dA, over here, and output dWL, dBL, the derivatives you need, as well as dA L minus 1, right, as follows. So that's how you implement the backward function. So just to summarize, take the input x. You might have the first layer, maybe has a ReLU activation function, then go to the second layer, maybe uses another ReLU activation function, goes to the third layer, maybe has a sigmoid activation function if you're doing binary classification, and this outputs y hat. And then using y hat, you can compute the loss. And this allows you to start your backward iteration. I'll draw the arrows first, I guess, so I don't have to change pens too much. where you would then have backprop compute the derivatives, compute, dw3, db3, dw2, db2, dw1, db1, and along the way you would be computing, I guess the cache would transfer z1, z2, z3, and here you pass back with dA2 and dA1. This could compute dA0, but we won't use that, so you can just discard that, right? And so this is how you implement forward prop and back prop for a 3-layer neural network. Now, there's just one last detail that I didn't talk about, which is for the forward recursion, we would initialize it with the input data x. How about the backward recursion? Well, it turns out that dA of L, when you're using logistic regression, when you're doing binary classification, is equal to y over a plus 1 minus y over 1 minus a. So it turns out that the derivative of the loss function with respect to the output, with respect to y hat, can be shown to be equal to this. If you're familiar with calculus, if you look up the loss function L and take derivatives with respect to y hat or respect
Oops.
to A, you could show that you get that formula. So this is the formula you should use for dA for the final layer, capital L. And of course, if you were to have a vectorized implementation, then you initialize the backward recursion, not with this, but with dA, capital A, for the layer L, which is going to be, the same thing for the different examples, right, over A for the first training example plus 1 minus Y for the first training example over 1 minus A for the first training example, dot, 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 down to the mth training example. It's 1 minus A of m. So that's how you implement the vectorized version. That's how you initialize the vectorized version of backpropagation. So you've now seen the basic building blocks of both forward propagation as well as back propagation. Now, if you implement these equations, you will get a correct implementation of forward prop and back prop to get you the derivatives you need. You might be thinking, wow, that was a lot of equations. I'm slightly confused. I'm not quite sure I see how this works. And if you're feeling that way, my advice is when you get to this week's programming assignment, you will be able to implement these for yourself and they'll be much more concrete. And I know there was a lot of equations and maybe some of the equations didn't make complete sense, but if you work through the calculus and the linear algebra, which is not easy. So, feel free to try, but that's actually one of the more difficult derivations in machine learning. It turns out the equations wrote down are just the calculus equations for computing the derivatives, especially in backprop. But once again, if this feels a little bit abstract, a little bit mysterious to you, my advice is when you've done the programming exercise, it will feel a bit more concrete to you. Although I have to say, even today, when I implement a learning algorithm, sometimes even I'm surprised when my learning algorithm implementation works. And it's because a lot of the complexity of machine learning comes from the data rather than from the lines of code. So sometimes you feel like you implement a few lines of code, not quite sure what it did, but this almost magically works. And it's because a lot of the magic is actually not in the piece of code you write, which is often, not too long. It's not exactly simple, but it's not 10,000 or 100,000 lines of code, but you feed it so much data that sometimes, even though I've worked in machine learning for a long time, sometimes it still, surprises me a bit when my learning algorithm works because a lot of the complexity of your learning algorithm comes from the data rather than necessarily from your writing, thousands and thousands of lines of code. All right, so that's how you implement deep neural networks. And again, this will become more concrete when you've done the programming exercise. Um, Before moving on, I want to discuss in the next video, want to discuss hyperparameters and parameters. It turns out that when you're training deep nets, being able to organize your hyperparameters well will help you be more efficient in developing neural networks. In the next video, let's talk about exactly what that means.
snowed on current layer, snowed on current layer, okay, snowed on previous layer. This subconcatenation of the previous layer should be applied by weight this skills on case animation of the previous layer. This equation of the previous layer, so the case the animation layer. And then bias in the current layer, equation in the current layer, the activation of the previous layer, activation function, and using the current layer. And concisely in the current layer is every previous layer is all measurement. We do summation for previous layers node activations to calculate earnings later. In more than previous layer affects every unique criteria in chain highlighting the it's true. The future will be scratching for the database algorithms and project vectors and right. Again, we want jump on L minus one layer. We do summation for this and shift with the bias. So we can calculate G1I. Mm-hmm. Maybe I'll show this. Okay, right, like that. Want to clarify following. So let's be the training example. Should we provide the clues necessary to move forward? Shall the extra not complete the limitation use the general symbol and to use this with the story? The limit is intentional. Let's close out on the task development. J, J maybe depends on Z. And Z depends on W. We can use channel.
Being effective in developing your deep neural nets requires that you not only organize your parameters well, but also your hyperparameters. So what are hyperparameters? Let's take a look. So the parameters of your model are W and B. And there are other things you need to tell your learning algorithm, such as the learning rate alpha, because you need to set alpha, and that in turn will determine how your parameters evolve, or maybe the number of iterations of gradient descent you carry out. Your learning algorithm has other numbers that you need to set, such as the number of hidden layers, so we call that capital L, or the number of hidden units, right? Such as N1, N2, and so on. And then you also have the choice of activation function. Do you want to use a ReLU or a tanh or a sigmoid or something, especially in the hidden layers? And so all of these things are things that you need to tell your learning algorithm. And so these are parameters that control the ultimate parameters W and B. And so we call all of these things below hyperparameters, because these things like alpha, the learning rate, the number of iterations, number of hidden layers, and so on, these are all parameters that control W and B. So we call these things hyperparameters, because it is the hyperparameters that somehow determine the final value of the parameters W and B that you end up with. In fact, deep learning has a lot of different hyperparameters. Later, in a later course, we'll see other hyperparameters as well, such as the momentum term, the mini batch size, um, various forms of regularization parameters, and so on. And if none of these terms at the bottom make sense yet, don't Don't worry about it. We'll talk about them in the second course. Because deep learning has so many hyperparameters, in contrast to earlier eras of machine learning, I'm going to try to be very consistent in calling the learning rate alpha a hyperparameter rather than calling it a parameter. I think in earlier eras of machine learning, when we didn't have so many hyperparameters, most of us used to be a bit sloppier and just call alpha a parameter. And technically, alpha is a parameter, but it's a parameter that determines the real parameters. So I've tried to be consistent in calling these things like alpha, the number of iterations, and so on, hyperparameters. So when you're training a deep net for your own application, you find that there may be a lot of possible settings for the hyperparameters that you need to just try out. So applied deep learning today is a very empirical process where often you might have an idea. For example, you might have an idea for the best value for the learning rate. You might say, well, maybe alpha equals 0.01. I want to try that. Then you implement it, try it out, and then see how that works. And then based on that outcome, you might say, you know what, I've changed my mind. I want to increase the learning rate to 0.05. And so if you're not sure what's the best value for the learning rate to use, you might try one value of the learning rate alpha and see the cost function j go down like this. Then you might try a larger value for the learning rate alpha and see the cost function blow up and diverge. Then you might try another version and see it go down really fast but converge to a higher value. And you might try another version and see it, see the cost function j do that. Then after trying a set of values, you might say, okay, it looks like the value of alpha gives me a pretty fast learning and allows me to converge to a lower cost function j, so I'm going to use this value of alpha. You saw in the previous slide that there are a lot of different hyperparameters, and it turns out that when you're starting on a new application, I actually find it very difficult to know in advance exactly what's the best value of the hyperparameters. So what will often happen is you just have to try out many different values and go around this cycle. Try out some value. Maybe you try 5 hidden layers with this many number of hidden units, implement that, see if it works, and then iterate. So the title of the slide is that applied deep learning is a very empirical process. An empirical process is maybe a fancy way of saying you just have to try out a lot of things and see what works. Another effect I've seen is that deep learning today is applied to so many problems, ranging from computer vision to speech recognition to natural language processing to a lot of structured data applications, such as maybe online advertising or web search or product recommendations and so on. And what I've seen is that first, I've seen researchers from one discipline, any one of these, try to go to a different one, and sometimes the intuitions about hyperparameters carries over, and sometimes it doesn't. So I often advise people, especially when starting on a new problem, to just try out a range of values and see what works. And in the next course, we'll see a systematic way. We'll see some systematic ways for trying out a range of values. Right. And second, even if you're working on one application for a long time, maybe you're working on online advertising, as you make progress on the problem, it's quite possible that the best value for the learning rate, the number of hidden units, and so on might change. So even if you've tuned your system to the best value of hyperparameters today, it's possible you find that the best value might change a year from now. Maybe because the compute infrastructure, be it CPUs or the type of GPU you're running on or something has changed. But so maybe one rule of thumb is, every now and then, maybe every few months, if you're working on a problem for an extended period of time, for many years, just try a few values for the hyperparameters and double check if there's a better value for the hyperparameters. And as you do so, you slowly gain intuition as well about the hyperparameters that work best for your problem. And I know that this might seem like an unsatisfying part of deep learning, that you just have to try a lot of values for these hyperparameters. But maybe this is one area where deep learning research is still advancing, and maybe over time we'll be able to give better guidance for the best hyperparameters to use. But it's also possible that because CPUs and GPUs and networks and data sets are all changing, and it's possible that the guidance won't converge for some time, and you just need to keep trying out different values and evaluate them on a Holocaust validation set or something, and pick the value that works for your problem. So that was a brief discussion of hyperparameters. In the second course, we'll also give some suggestions for how to systematically explore the space of hyperparameters. But by now, you actually have pretty much all the tools you need to do the programming exercise. Before you do that, just want to share with you one more set of ideas, which is I often am asked, what does deep learning have to do with the human brain? So, what does deep learning have to do with the brain? At the risk of giving away the punchline, I would say not a whole lot. But let's take a quick look at why people keep making the analogy between deep learning and the human brain. When you implement a neural network, this is what you do: forward prop and back prop. And I think because it's been difficult to convey intuitions about what these equations are doing, really gradient descent on a very complex function. The analogy that is like the brain has become really an oversimplified explanation for what this is doing. But the simplicity of this makes it, kind of seductive for people to just say it publicly, as well as for media to report it, and it's certainly caught the popular imagination. And there is a very loose analogy between, let's say, a logistic regression unit with a sigmoid activation function, and here's a cartoon of a single neuron in the brain. In this picture of a biological neuron, this neuron, which is a cell in your brain, receives electric signals from other neurons, maybe X1, X2, X3, or maybe from other neurons, A1, A2, A3. Does a simple thresholded computation, and then if this neuron fires, it sends a pulse of electricity down the axon, down this long wire, perhaps to other neurons. So there is a very simplistic analogy between a single logistic unit, between a single neuron in a neural network, and a biological neuron like that shown on the right. But I think that today, even neuroscientists have almost no idea what even a single neuron is doing. A single neuron appears to be much more complex than we are able to characterize with neuroscience. And while some of what it's doing is a little bit like logistic regression, there's still a lot about what even a single neuron does that no human today understands. For example, exactly how neurons in the human brain learns is still a very mysterious process. And it's completely unclear today whether the human brain uses an algorithm that does anything like backpropagation or gradient descent, or if there's some fundamentally different learning principle that the human brain uses. So when I think of deep learning, I think of it as being very good at learning very flexible functions, very complex functions, to learn X to Y mappings, to learn input output mappings in supervised learning. And whereas the is like the brain analogy, maybe that was useful once, I think the field has moved to the point where that analogy is breaking down, and I tend not to use that analogy much anymore. So that's it for neural networks and their brain. I do think that maybe the field of computer vision has taken a bit more inspiration from the human brain than other disciplines that also apply deep learning. But I personally use the analogy, to the human brain less than I used to. So that's it for this video. You now know how to implement forward prop and back prop and gradient descent even for deep neural networks. Best of luck with the promo exercise, and I look forward to sharing more of these ideas with you in the second course.
This is the answer for today's recording. Before I stop recording, I'm going to recap first. So what I learned today is quite simple than previous recording. I just learned here what is the building blocks of deep neural networks and how we can implement a forward propagation and backward propagation in deep neural networks. So if we assume that we have such a deep neural network with a layer with four layer deep neural network, when we compute a forward propagation, we use previous previous activation units from previous layer, and we applied it. We multiplied by previous current weight with the previous activations to calculate the current activations. Yes. And as we've already seen this in the logistic regression topics, when we calculate one unit, we calculate the g first to give it as an input of activation function. So we also cache g for the backward propagation, and also for implementation purpose, we also store w and b parameters for the implement for in the cache. At the same time, when we compute the backward propagation in deep neural network, the input will be dA, which is current layer, which is activation value of current layer, and cache GL, and the output will be the previous layer of derivatives of DAL minus one and DWL and BBL and so on. So this is an analogy of how the forward propagation and backward propagation works in the neural network. As I already said, we have activation from previous layer, and by using the current layer's weights and bias, we can compute what is the exact current layer's activation. And by using the derivatives of current layer, we can compute the previous derivatives of current activation of in the previous layer. Also, as output of backward propagation step, we can compute what is the dW of current layer and what is the dBl in the current layer. And this is its whole overview in the deep neural network. about how to compute the forward propagation and backward propagation. And this is the actual equations by using to compute those. And there's a learning material. Let's see, like here, professor unloaded a derivation, but I think it takes quite a time to read all these posts, so I delayed it for the last time of this recording. And for the last, we compared what is the parameters and what is the hyperparameters exactly in neural network. And the parameters is we've already seen is a W and B, which is the parameters used for actual computation for the and backward probe. But hyperparameters is like learning rate and number of iteration and number of hidden layers and number of hidden units and like a choice of activation function among ReLU and tanh and sigmoid activation like and so on and other activation functions. All of these hyperparameters is not directly related to computation forward and backward probe itself. And however, these hyperparameters somewhat control the result of actual parameter like W and B, so we need to adjust them appropriately during the empirical process. So modern neural network process following these cycle, we made idea and we code them and we do experiment. And if the result is not the result that we expected, we need to adjust these hyperparameters to improve the result to attract them into what we expected before. Okay, that's all for today's recording, and thanks for your watching.